Welcome to our structural steel design masterclass. So I am so excited to have you in this course and in this journey of structural steel design. So I'm very happy, and I believe that at the end of this course you will learn a lot and you will understand the basic and the principle that govern the design of steel structure according to Eurocode 3. So we want to kickstart our design process. So we look at our course outline. So today we want to learn the, the concept of simply supported restraint beam and how we can design it. Now, steel design is not as easy as some of us think, especially when you don't understand the basic principle that govern it. Especially, we must understand that that beam is a bending member. So when you are designing steel, you must consider a lot of those basic check that the code require us to to undertake. And you must also understand what type of beam are you designing, or what type of steel are you designing. Are you designing a restrained beam? Are you designing unrestrained beam? Because though the check are similar, but there are some little disparities in their design process. So today we want to understand the design concept of simply supported restrained beam. Okay, now what is a restrained beam? That is the first question that you must ask yourself. What is a restraint beam? A lot of people just pick a design software and start designing without really understanding what type of structure that they are designing and the principle that govern the design of that structure. So we want to understand what a restraint beam is and what are those design process that is required when we are designing restraint beam. So from this simple definition, a restraint beam is a structural beam whose movement, rotation, lateral deflection, or vertical displacement is restricted at its support or along its length, preventing it from freely bending or twisting like a simple beam, opened by being rigidly fixed like a fixed end beam or connected to a slab. Connected to a slab. Now, there is a key word here, connected to a slab. Now, before I want to further explain what this means. So let's go to let's go to the orthodox robot. Now, this beam is a restraint beam, and this one here is a restraint beam. Why is it a restraint beam? Because the flange of this beam, the top flange of this beam, is being uh, the top flange of this beam is prevent the movement of this beam, especially the top flange, is being prevented by the slab. In other words, there is a restraint at the top flange of this beam. So this beam is also known as secondary beam. This is the primary beam. This is the primary beam. But this one is known as the secondary beam. So this secondary beam is known as a restraint beam because the top flange is being restricted or being prevented from lateral movement. So meaning that the top flange is fixed. This top flange is being fixed as a result of the placement of the slab. So this beam cannot move laterally. It cannot move laterally because the top flange of this beam is restrained. So, meaning that secondary beam are usually designed as restrained beam, while primary beam are designed as unrestrained beam. So we might not really say much about the unrestrained beam in this model until when we want to design the unrestrained beam. So you must understand that a restrained beam is that beam whose top flange is fixed or restrained or restricted from lateral movement. That is what a restrained beam. So let me also show you the second picture here. Now, when you look at this top flange is being prevented from movement. It's being prevented from lateral movement, rotational movement. How? Because of the introduction of this concrete, and we have the metal steel deck. So now this is a connector stud, and this connector stud is welded onto the top flange, prevents which prevents this beam from moving either laterally or maybe vertically. So this is example of a restrained beam. This is example of a restrained beam. So we go back. Now, this restraint means the beam can only deflect vertically with its top compression flange prevented from buckling sideways. So you can see from what we have just explained that the beam can only deflect vertically. So there is a deflection vertically, but when it comes to the top compression flange, it is being prevented from buckling, which is sideways movement, or what we may call the lateral torsional buckling, allowing for greater load capacity and stable performance common in composite structure. Now, we can design this beam also as a steel composite beam. So meaning that we can design a secondary beam or a restraint beam as a steel composite beam, and design it as a steel composite beam as well for economy. But in this very model, we want to design it as a restraint beam. Maybe as we proceed, we are going to design this beam as a steel composite beam. So a restraint beam has its compression flange, usually the top flange, held in place laterally, preventing this type of buckling. Now, this allowed the beam to reach its full plastic moment capacity, its maximum strength in bending before felling. So the process of fixing the compression flange, top flange, allowed the beam to reach its full plastic moment capacity. So full lateral restraint is provided by a positive attachment of floor system to the top flange of the simply supported beam. So you can now see that when we are talking about a restraint beam, it has to do with a beam that a floor system is attached to the top flange of the simply supported beam. Now let me also show you something here. Now, when you look at this beam, when you look at the direction of the the reinforcement, you see that the reinforcement is placed on this direction, meaning that the load is transferred to this beam on this direction. Now, this is an example of a secondary beam, which is also a restraint beam. So the floor slab is being carried by this beam. The arrangement of the load is on this beam. So this is an example of a restraint beam, which is also a secondary beam. This is example of a secondary beam. This example of a secondary beam. So these are secondary beam. But when you look at this, these are primary beam. Now, why is it a primary beam? Because this very beam here carries the point load that is from the secondary beam. So this is a primary beam, which we can also call it as an unrestrained beam. But our focus today is on the restrained beam. So this is how you can identify a restraint beam in your layout. So you look at this is a restraint beam, this is a restraint beam, a restraint beam, this is a restraint beam, this is a restraint beam. So this is example of restraint beam because they carry the load from the slab. So meaning that we can design this as a steel composite beam. We can as well design this as a restraint beam. So meaning that the primary beam is usually designed as unrestrained beam, while the secondary beams are usually designed as restrained beam. Okay, so we proceed. So we said here that full lateral restraint is provided by positive attachment of floor system to the top flange of the simply supported beam. So beams which are unable to move laterally are then restrained. So these are further explanation of what we mean by restraint beam. Okay, now that we have understand what a restraint beam is, so let's look at the design process for Eurocode 3. So we have 4 basic factors that must be considered when we are designing a restraint beam. So the third one is not really problematic because the third one is applied to a beam that has multiple point load. Example, like the plate girder. So it's not really applicable to the normal beam. So we are going to focus on 3 factors, which is the bending moment resistance, the shear resistance, the serviceability resistance. So when you are designing a restraint beam, these are, after the loading and the analysis, these are the check that you need to consider. So you need to consider the bending moment resistance, the shear resistance, and the serviceability. Now, the bending moment resistance has to do with the ratio of the applied moment to the resisting moment. And the code says that it must be less or equal to 1. It must be less or equal to 1. Then the same thing is also applicable to the shear resistance, which has to do with the applied shear and the resisting shear. And the code also says that it must be less or equal to 1. Then the serviceability has to do with the deflection. So there is a limit in which the structure must not exceed in terms of deflection. So we are going to see this in a few moments. Okay, so the bending check. I think okay, the bending check. So we have, this is our applied moment and this is our resisting moment, and it must be less or equal to 0. Then for the shear check, this is our applied shear, this is resisting shear, and it must be less or equal to 0. So let's quickly go to this material for us to have an elaborate understanding of what we are doing. Okay, so now for the restraint beam, still designed to Eurocode 3 restraint beam. So we have already considered what a restraint beam is. So these are the summary of it. So we look at the numbers of factors to be considered. So we look at the bending moment resistance. Now, in the bending moment resistance, you go to clause 6.2. So clause 6.2 covers the cross-sectional resistance. Now, clause 6.2.5 deal with the cross-sectional resistance for bending. So this particular clause, okay, let me say, clause 6.2 covers the cross-sectional resistance. But specifically, the clause that deal with the cross-sectional resistance for bending is clause 6.2.5. So when you go to Eurocode 3, go to this clause, the material is there, so you will have access to it. So when you go to this clause, this particular clause deal with the cross-sectional resistance for bending. So then clause 6.2.4 gives you the equation 6.12, which states that the design moment must be less than the design cross-sectional moment resistance. Now, what this entails us is that the design moment must be less than the design moment must be less than the design cross-sectional moment resistance. So the moment resistance must be greater because this is what is resisting the applied moment. So equation 1.6.12 says that the applied moment all over the resisting moment must be equal or less than 1. Now, the equation to calculate the resisting moment is dependent on the class of the section. So what this means is that we, in our steel design classification, we have the class 1 and we have our class 2. So this resistance or resisting moment depends on which of the class or which of the class your cross section belongs to. Does it belong to class 1 or class 2? Is it a class 1 section or class 2 section? So it will depend on it. So if it is class 1 and 2, then this is the equation that you are going to apply. You see how I can. So you are going to apply equation 6.13 if it falls between class 1 and class 2 cross section. So during our design demonstration, we will look at how we can arrive at this classification. Okay, so for class 3 cross section, this is how you calculate your resisting moment. Your resisting moment. This is how you calculate it. So this is the formula for it, which is equation 6.14. Then for class 4 cross section, this is also the formula for it. Okay, so after you have checked the bending resistance and the ratio is less or equal to 1, then you know that your bending moment resistance is okay. So the next check is your shear resistance check. So this one is also clause 6.2, which also covers the cross section resistance. Then this one specifically, clause 6.26, deal with the cross sectional resistance for shear. Remember that clause 6.2.4 remember that clause 6.2.5 deal with the cross sectional stand for bending. So you take note of this. This is for bending. Take note of this. This is for shear. So clause 6.26 deal with the cross sectional resistance for shear. Then clause 6.26 equation 6.17 state that the design shear, which is also the applied shear, must be less than the design plastic shear resistance of the cross section. So this is the design plastic shear resistance of the cross section given by this notation, and this is the equation. So this, whatever that you have here, must be less or equal to 1. So look at the summary. Calculate the shear area AV, substitute the value of AV into the equation 6.18, then to get the design plastic shear resistance, then carry out the cross-sectional plastic shear resistance by checking the equation 6.17 to be satisfied. Then the same thing also is applicable to the bending moment resistance. Summary of it: determine the design moment, then choose a section and determine the section classification, then determine the resistance moment using equation 6.13 for class 1 and class 2 cross section. Now equation 14, 6.14 for class 3 cross section, and equation 6.15 for class 4 section, and ensure that the correct value of W, which is the section modulus, is used. So carry out the cross-sectional moment resistance check by ensuring equation 6.12 is satisfied. Then the next check is the next. This is the formula for the resisting shear. This is how you calculate the resisting shear for the design. This is how you calculate the resisting shear for it. So this is the AV. You have to calculate the AV. So we have the formula for calculating AV. Now the next check is the deflection check. We have this deflection check. Now when you look at here, you see that different load, here require different formula for deflection. So when you have a point load, this is the formula that you are going to use to check for the deflection. So when you have a point load, this is the formula that you're going to check for the deflection. Now when you have a UDL, this is for some of us that are very familiar with this formula, you know that this formula is what you are competent with this formula. Now, this formula is only applicable when you have a UDL. But when there is a point load, then this formula is not applicable. Then you have to combine the formula that has to do with the point load. Okay. So the same thing is also, now this one is when the beam is simply supported. The deflection here is when the beam is fixed. So you can see here that under this one, we have WL cube all over 48 EI. Then for the fixed, we have WL cube all over 192 EI. Then for the UDL, we have fixed end, this is the formula for it. Now, in a place where we have the beam to be cantilevered, this is the formula for the deflection. Then for where you have a prop beam, meaning that one side is fixed and this other side is prop, and it is a UDL, this is the formula for you to check the deflection. Okay, so the maximum deflection calculated must not exceed the deflection limit. So the deflection limits are not given directly in Eurocode. Instead, reference must be made to the national annex. Now, what this means is that checking of deflection in Eurocode is not being given. There is no straight clause that you can go in Eurocode and just pick the formula and calculate for deflection. Instead, what they do is that they allow you to make reference to your national annex. So meaning that every country must have their own national annex. Now, what is national annex? National annex are those nationally agreed principle or design information that is suitable to a particular location or a particular country. So in UK, they have their national annex, those national determined parameters that they use in doing their design. So in every country, it is expected that they should have their own national determined parameters that they use in doing their design. So design situation deflection limit. So in cantilever, your deflection should not be more than L over 180. This is the deflection limit. So any value that you have that is more than L over 180, then that deflection is not satisfied. Then beam carrying plaster of other brittle finish. So the deflection limit here is span all over 360. Then other beam except polyline and sheeting rail. The deflection limit here is span all over 200. Then polyline and sheeting rail to suit the characteristic of a particular cladding. Okay, so I think we will demonstrate this more when we move to the actual design process. Okay, so in our next video, we are going to do Excel template calculation demonstration. So the beam that we are going to consider the restraint beam that we're going to consider will have a span of 8 meters. I think we are going to design this beam. We are going to design this. So let's check let's confirm the span of this. So this is 8 meters. So we are going to design this beam. So we are going to design that beam. So the top flange of the beam is fully restrained with concrete slab, fully grouted and covered with structural screed. So when you look at this drawing, you will see that here we have a slab, and the slab is spanning. The slab is spanning on the direction of the direction. This is the direction of the main reinforcement. So meaning that this constitute load to this beam, and this constitute load to this beam. So when you consider the condition for the restraint beam, you see that the top flange of this beam is completely restricted, or is completely restrained, so which made this beam to become a restrained beam. So the bay width here is 2.8. So let's look at the bay width here. Let me okay, so this will be 2875. So this will be 2875. 2875. 2875. So the following check will be performed. So number one, we are going to perform the bending moment resistance. Number two, we are going to consider the shear resistance. Then we will look at the serviceability, which has to do with the deflection. Then after we have done the Excel template calculation demonstration, we will also do the software demonstration to cross-check if what we have done in the Excel is correct, or if what we have done in the Autodesk Robot Structure Analysis professional software is that or give us the same result as what we have in the Excel template. So we will be able to judge the two design method that we have used. So thank you very much for your time, and I believe that you have learned something. So see you in our next module. Bye.